Magnets, these physical marvels capable of attracting metals and widely used across modern industry, electronics, transportation, and healthcare, have long evolved beyond the simple lodestone. Today, there is a wide variety of magnets, including neodymium iron boron, NdFeB, ferrite, and samarium cobalt, SMCO, each involving complex material science and highly industrialized manufacturing processes. In a modern magnet factory, the journey from rare earth raw materials to finished magnetic blocks is a comprehensive demonstration of material purification, composition adjustment, high-temperature sintering, mechanical processing, and electromagnetic performance testing. Today, let's take you inside a magnet factory to explore how a tiny magnet carries the invisible force that powers the modern technological world. The first step in magnet manufacturing is raw material preparation. Depending on the magnet type, the factory procures various rare earth or metal powders such as neodymium, iron, boron, samarium, cobalt, strontium, and iron oxide as base materials. For example, producing NdFeB magnets requires high-purity neodymium metal, metallic iron, and alloyed boron powder, which are melted into a uniform alloy ingot using a vacuum induction furnace. The smelting process must be conducted in an oxygen-free environment to prevent oxidation that could impair magnetic performance. The alloy ingots are then crushed and pulverized into fine powder less than several tens of microns, and further homogenized in a ball mill under argon protection. The key step in forming magnets from powder is pressing and shaping. During this stage, the magnetic powder is placed into molds and subjected to magnetic field alignment under an external magnetic field, aligning the magnetic moments in a single direction to enhance the magnetism of the sintered body. Pressing typically employs either isostatic or die pressing, forming a dense but still fragile green compact. This green compact then enters a high-temperature sintering furnace, where it is sintered at over 1000 degrees Celsius for several hours, fusing the particles into a dense body with about 15% volume shrinkage. The sintering process determines the microstructure, porosity, and energy product of the magnet, making it one of the core steps affecting performance. The sintered magnet is a semi-finished product, not yet at its final dimensions or precision. It undergoes mechanical processing, including wire cutting, cylindrical grinding, surface grinding, and drilling, to refine the magnet into regular cubes, cylinders, rings, or custom shapes, with tolerances controlled within microns. At this stage, the magnet has not yet exhibited magnetic properties and must undergo a magnetization process to gain strong adhesive force. The magnetization equipment is usually a high-energy pulse magnetic field generator composed of coils, which delivers a current of tens of thousands of amperes through the coil in an instant, applying a powerful magnetic field to the magnet and fully aligning its internal magnetic domains, thus imparting magnetism. The magnetization process is not the end. The factory must also conduct a series of performance tests, including measurements of remanence, coercivity, and energy product. Some high-end magnets must also undergo high-low temperature cycling, corrosion resistance, and demagnetization resistance tests to ensure stable performance in various application scenarios. Magnets that pass the tests are sorted and packaged according to size, magnetic orientation, and coating type, such as nickel, zinc, or epoxy coatings. During packaging, care must be taken to prevent magnets from attracting and colliding with each other by using plastic separators and magnetic shielding materials to avoid demagnetization or damage during transport. Some magnet factories also have special product lines for manufacturing custom-shaped magnets or magnetic assemblies. For instance, magnet steel components used in electric vehicle motors, wind turbines, and MRI equipment require combining multiple magnets with metal structures using high-strength adhesives or mechanical fixtures into complex assemblies. These products require considerations of mechanical strength, heat conduction, and electromagnetic compatibility, typically employing robotic assembly and 3D magnetic field simulation optimization to ultimately form magnetic assemblies that meet customer technical specifications. From an environmental perspective, modern magnet factories have adopted exhaust purification systems, water recycling systems, and rare earth recovery equipment to treat and recycle dust emissions, acidic or alkaline wastewater, and scrap materials, reducing environmental impact and improving resource utilization. Especially since rare earth metals are expensive and scarce, even trace dust and waste liquids must be recovered and purified using chemical precipitation or ion exchange technology, further lowering production costs and reducing dependency on mineral resources. Transforming non-magnetic powders into powerful finished magnets is the result of the combined efforts of high temperatures, magnetic fields, precision machining, and intelligent testing. Whether it's a small fridge magnet or a permanent magnet rotor in a high-speed rail motor, every piece of magnet is the crystallization of tightly controlled processes in a modern factory. So the next time you see a piece of metal sticking to a magnet, take a moment to think about the high-temperature furnaces, vacuum environments, and micron-level processing it has gone through. This tiny magnet embodies the tremendous power of materials science and industrial civilization. Subscribe to our channel, and in the next episode, we'll continue unveiling more industrial manufacturing miracles hidden behind everyday objects.